How does wavelength affect transmission lines? Imagine you're trying to send a message across a busy highway. The way your message travels depends a lot on the distance and speed. That's similar to how electrical signals move along transmission lines. Wavelength is a key factor in this process. It's the distance a signal travels during one complete cycle of its wave. When the wavelength is very long compared to the length of the transmission line, the line acts like a simple wire. The signals move smoothly, and we don't need to worry about wave effects. But as the frequency of the signal increases, the wavelength gets shorter. When the line length becomes a significant part of the wavelength, strange things happen. Voltage and current no longer stay uniform along the line. Instead, they form standing waves with peaks and valleys. These are caused by the wave bouncing back and forth, creating reflections. This can lead to signal loss or distortion. The line then behaves more like a waveguide, with energy traveling in specific patterns. This is especially true for high-frequency signals used in communication systems or control signals in power grids. The physical size of the line and the electrical properties, like inductance and capacitance, influence how the wave moves. If the line isn't properly designed, reflections can cause ringing or power loss, which reduces efficiency. For power transmission at 50 or 60 Hz, the wavelength is enormous, thousands of miles, so effects are minimal unless the line is extremely long. But for high-frequency signals, such as those in data communication or control signals, the wavelength can be just a few meters or less. That's when transmission line effects become very important. Engineers need to match impedance and use proper terminations to prevent reflections and signal loss. They also consider the propagation velocity, which is how fast the wave moves through the line. This depends on the physical construction of the line and its electrical properties. In short, wavelength determines whether a transmission line behaves like a simple wire or a complex wave system. It affects how signals are transferred, how much power is lost, and how well the system works. Understanding this helps engineers design better power systems and communication networks, making sure energy and data get where they need to go without issues.